Well, welcome back. This chapter, chapter 13, involves solving equations by factoring. And for those of you that were wondering where factoring was going, this is where it's leading us.
Right. One of the main reasons we need to know how to factor is it's probably the easiest way to solve quadratic equations, that is, equations in which the highest exponent is 2. So once we know how to factor, we can solve these pretty quickly. In intermediate algebra, you'll learn some other techniques for solving these equations, but factoring is usually the fastest.
Yes, well, let's go ahead and get started. This first problem here, and it might be helpful if you have your rules sitting next to you, the summary of rules on factoring, but the first rule of factoring was always to take out something common. So when you look at this problem, you should notice that there is an x that you can take out of each part. Once you factor out that x, which is our greatest common factor, you then say, okay, what will go in here? Well, x times x is x squared, and x times negative 10 is negative 10x. Now, this is the halfway point. Now we're going to set each piece equal to 0. Now, the principle that we follow for this is the rule where if you have any two terms multiplied together that give you 0, we know that either x must equal 0 or y must equal 0. So our x and y in this problem are x and x minus 10. If either of these is 0, then this whole equation will be 0. So now we're going to solve this. This one is finished. There was nothing to do. And on this side, we need to add 10 to both sides. So we come up with x equals 10 and x equals 0. These are the two solutions to this equation. Bill, did you want to add anything to that?
No, I just wanted to point out that notice that in this case, when we're factoring, we still have that equals 0 on the right side of the equation, because now we're looking at equations. We're not just doing these problems purely as factoring exercises, but you really don't do anything different. Just keep bringing down the equals 0 on the right side, and then, as Jerry said, once you've done the factoring, set each factor equal to 0 and solve those equations. And the thing you'll notice in these problems is that now we'll usually have two solutions to the equation instead of there just being one solution.
Now, there is one thing, if you want to go back and check, 0 is easy enough to do in your head. You would have 0 squared minus 10 times 0, which is 0. Of course, that equals 0. The 10, I'll write out 10 squared minus 10 times the 10 equals 0. And again, you see 100 minus 100 equals 0. So remember, if you're not sure about your answers, or you're not sure about your factoring or the signs, substitute them back in, check them out. Now, on the second problem over here, this is a trinomial. There's nothing common in each term. So first, write out all those factors of 12, which are 1 and 12, 2 and 6, 3 and 4, not 3 and 6. There we go. And then you ask yourself, what are the factors of 12 that add to give me negative 7? Well, clearly it's the last two we came up with, the 3 and the 4. So, factoring this, we end up with x, 3 and 4. And since we're adding and our middle term is negative, both of these must be negative. Now we're going to take each piece, or each factor here, and set it equal to 0. So x minus 3 equal to 0, and x minus 4 equal to 0. Adding 3 to the other side, you end up with x equals 3. And over here, we're going to add 4 to the other side, and we get x equals 4. And those are our two solutions to that one. So let's look at some that might be a little bit more difficult. Okay, this problem, you'll notice something different. This is our first problem that is not set equal to 0. We have x squared equals 49. In order to start this problem, we first need to set it equal to 0, so we need to bring 49 to the other side. So our new equation becomes x squared minus 49 equals 0. Now, using your rules for factoring, you'll notice this is a difference of two squares. So, if you recall, factoring a difference of two squares involves taking the square root of x squared, which is x, the square root of 49, which is 7, and then putting in a plus and a minus. So finishing out this problem, set x minus 7 equal to 0, x plus 7 equal to 0, and then solve. Some of you will start doing this part in your heads. Others of you might want to continue to write this out until you're very comfortable with the signs of our final answers.
Right, and let me just say something right here. You shouldn't try to factor any equation until you have all of the terms by themselves on the left side and 0 on the right side. So in some cases, you might be able to factor with what the original equation looks like, but you never want to do that. The only time you want to factor is if all of the terms are by themselves on the left side and there's a 0 on the right side. Once there's a 0 on the right side, it's safe to factor and then go ahead and solve the equation.
Yes, the zero product property, which I believe you'll find in your textbooks, definitely alludes to that. We can't have these set equal to anything other than 0 to solve them by factoring.
That's right.
So this next problem deals with a little bit tougher of factoring. Step 1, again, we want to bring the 4 over. And since we have all these terms, remember, we want them in descending order of degree. So the minus 4 is going to be the last term before the equal sign. Now, using our rules for trinomials with coefficients at both ends, start, multiply the first two together, you get 12. Now, all the factors of 12 are 1 and 12, 2 and 6, 3 and 4, and we want the factors that subtract to give us that 1 in the middle. So we're going to choose the last two right here. Go ahead and put the x's on them, and since we want a negative 1 in the middle, we want the 4 to be negative and the 3 to be positive. That way when you subtract them, you end up with a negative 1. So now carry down the 3x squared. Substitute these two terms for the middle, and then carry down that minus 4. Okay, now using the grouping method, group the first two and the last two. Out of the first two, we can take out 3x. And we're left with x plus 1. Out of the second two, remember when that third term's negative, we want to take out a negative, and we can take out negative 4, and again we're going to come up with x plus 1. Remember, negative 4 times x is negative 4x, negative 4 times 1 is negative 4. So we finally get this thing factored by taking out the x plus 1's, and then the 3x minus 4 goes in the other parenthesis. Setting each piece equal to 0, x plus 1, and 3x minus 4 gives us the following. Moving 1 over becomes negative. Moving 4 over here, we get 3x equals 4, but this one we have one additional step. We still have to divide by 3, so we get x is equal to 4/3. So, a lot more cumbersome, a lot more work, but a fun challenge.
That's right. And again, don't be scared of these problems. Just treat each step separately. Go ahead and just do the factoring, and the factoring will take a couple of steps. But again, once you've done the factoring, if you just set each term equal to 0 separately, usually that part of solving that equation will be relatively easy. You'll end up with the two answers. These problems, in a way, are a really good review of a lot of what you've done so far in the course because they combine so many things, and there are usually at least 1 or 2 problems like this on the exit test. So this is one of those things you just got to be able to do.
Good point.
I'm sorry, I'm jumping the gun. Jerry, go ahead.
This last problem, again, involves our factoring, and we wanted to give you this one because it kind of reviews all of factoring again. Remember, at first you might think, well, I've multiplied the 2 and the 20, and we'll say, no, don't skip that first rule that says take out what's common. Well, in this problem, you have a 2 that is common in each term. So you first divide out or factor out the 2. Then you see this trinomial in here. Much easier trinomial to work with. I'm going to write out my factors of 10 over here, which are 1 and 10, 2 and 5, and then I ask myself, what factors of 10 subtract to give me 3? Well, it's the 2 and the 5. So continuing on with the factoring, I now end up with an x and an x, a 2 and a 5, and then I want a positive 3. So since I'm subtracting, I want the 5 positive and the 2 negative. So now the question comes up, what do you do with the 2? Well, the 2 doesn't have an x with it, so technically it's not an equation that can be solved. So we're just going to set x minus 2 equal to 0 and x plus 5 equal to 0, giving us the final answers of 2 and negative 5.
Now, if I can borrow the pen for a second, if you're confused in this step by the fact that Jerry didn't set the 2 equal to 0, notice that when you get to this step, if you wanted to, since 2 is a number, I could just divide both sides by 2. If I did that, 2 divided by 2 would just be 1. That would just leave x minus 2 times x plus 5. Sorry about that 2, it's a little hard to read. And 0 divided by 2 is 0. And now I would just set the x minus 2 equal to 0 and the x plus 5 equal to 0 the way that Jerry did. So the bottom line is this. If you have any terms in the front, we don't set terms equal to 0. We only set terms that involve x equal to 0 because that's what we want to do, solve for x.
Yes. Let's move on to proportions.
Okay, what I started to say before was you may remember that we had a section a couple chapters ago where we set up proportions, and at the time we told you later on we'll tell you how to actually solve these equations. So that's what we're learning how to do now. Now we're going to actually look at these equations that we set up in the earlier chapter and figure out how to actually solve for x in these problems.
Okay, our first problem here, very simple proportion to work with. We have 1/3 equals x over 27. Whenever you have a fraction equal to a fraction, whether you know it or not, the cross products must be equal. So we in turn cross multiply to solve this equation. So we end up with 3 times x equals 1 times 27, or simply 3x equals 27. Now to finish solving that equation, you realize that we just divide both sides by 3 to get our final answer of x equals 9. And that problem is finished. Our second one's a little bit more cumbersome only because when we cross multiply, we end up with something other than just x. X times x is x squared. 2 times 8 is 16. This is a quadratic equation. We know this because of the square on the x. So in order to solve this, just as we were doing earlier, our first step is to bring 16 over. When we do this, we end up with a negative 16. Now, going through your factoring rules in your head or looking at them on paper, you realize that is a difference of 2 squares that we can factor into x plus 4 and x minus 4. Solving this by setting each piece equal to 0 gives us the following. X equals negative 4 and x equals positive 4. All right, let's look at our next ones. Our next problems kind of involve something unique to this course, but not unique, hopefully, in your backgrounds. The good old Pythagorean theorem. Hopefully you remember it from geometry, right?
Right.
Bill?
If you've forgotten everything else about geometry, our experience is that a lot of times this is the one thing that students might remember. On top of everything else, though, these are relatively common problems to see both in this class and in intermediate algebra. So if you haven't seen the Pythagorean theorem before, we'll go ahead and review it for you now.
Okay. The Pythagorean theorem states that the hypotenuse squared, which in this problem is x, equals the sum of the 2 legs squared. We'll identify those as A and B. We realize these variables are different in almost every book that you see, but in summary, the hypotenuse is what my students call the slanty side. It's not the one straight up or horizontal, it's always the slanty side.
Or if you want, you can also think of it as the long side, because it will always be the longest side of the right triangle.
And when you're drawing a picture, if you put your right angle in here, it's always the side opposite the right angle. So hopefully with all 3 of those definitions, you're comfortable now identifying the hypotenuse. So going back to this problem and solving it, we're solving for the hypotenuse in this problem. So we set it up, x squared equals each leg squared or the sum of each leg squared. Okay, now squaring, can't square x, it's already squared. Squaring 2, you end up with 4, and squaring 4, you get 16. So this gives us x squared equals 20. Now, previously we would bring that 20 over and solve this problem. At this point in the course, we're going to show you an alternative method to solving this, which is the square root property. Now that you've learned radicals in Chapter 12, this will take us a little step further into why we need to know how to simplify radicals. So, simplifying this, we're first going to square root both sides. Square rooting an x squared, we learned, gives us just x. The square root of 20, however, is not a perfect square, but we have learned how to simplify those. So if you think of your list, what perfect square divides into 20, you might think of the 4. And we know that 4 times 5 gives us 20. So what's our final answer? Well, once you take the square root of 4 and make it a 2, that leads you to the final answer of x equals 2 square root of 5. Okay, let's do one more.
All right.
Okay, in this problem, we are given the hypotenuse as a number 8. Again, remember the hypotenuse is opposite the right angle. So our equation is 8 squared equals x squared plus 7 squared. 8 squared is 64. Rewrite x squared, and then 7 squared is 49. Now, subtracting 49 from both sides gives us the following equation. 15 equals x squared. And again, using the square root property, we can square root both sides because we are solving for x, not x squared. We end up with the final answer of x equals the square root of 15. You might ask, why the square root of 15? Go back to that perfect squared list and you'll find that there are no perfect squares that divide 15.
That's right. There's one thing about this that you might find confusing, so I just want to talk about this for a second. Back when we had a problem like this that we had on the previous page, it was x squared equals 16. You might ask, why can't we solve a problem like that using the square root property? And we can actually, if you remember one thing. Every number actually has 2 square roots, both a positive square root and a negative square root. In particular, when, as Jerry says, we take the square root of both sides, it's important to remember that 16 has 2 square roots, both positive 4 and negative 4, because positive 4 squared is 16 and negative 4 squared is 16. You may say to yourself, aha, though, when Jerry was going ahead and doing those problems involving Pythagorean theorem, he just wrote down the positive square root. Why did he leave out the negative square root? And the reason why is simple. For those problems involving the sides of a triangle, we're measuring the length of a side, and it doesn't make sense for length to be negative. So in those problems, even though technically every number does have 2 square roots, we're actually only interested in the positive square root because it does represent the length of the side of a triangle. This, however, is also a way you could have solved the problem x squared equals 16 rather than rewriting it as x squared minus 16 and then factoring it. If you go back and look at that problem, you'll see that we got the same answers here that we got back there. Again, you can do this problem whichever way seems easier to you.
Well, Bill, that wraps up this chapter.
All right, we only have one chapter left to go, so we look forward to seeing you in chapter 14.
That's right.